Hey everybody, welcome back to Chapter 7, Section 3. This is Part 3. I promise this is the last part of this section. Here we're going to talk specifically about inverses of logarithms, okay? So let's talk about, the definition of a logarithm, what it means. Remember, in the last video, I mentioned that logs are inverses of exponential functions, and exponential functions are inverses of logs. Okay, so that being said, we have this property right here. You take the logarithm function like log base b of x. It's the inverse of b to the power of x. Okay, we covered that, in previous videos. So if you take log base b and multiply it times b of x, in other words, you multiply log by the exponential function, you're just going to wind up with x. Alright? Similarly, if you take the exponential function first and raise it to the power of log base b of x, you still just get x. That's what it's saying. That sounds really confusing. It's like, what? I don't understand this at all. So let me put it to you this way. Logs and exponential functions they cancel each other out. Okay? So if you look at this, if you have log base b and then you have b to the power of x, you have those b's in common. The whole thing would just go away and you're just left with the exponent x, whatever's there. Same thing here. If you have b and log base b, they would just cancel each other out. You just have x left over there. That might make a little bit more sense, but and maybe it'll help to look at the graph. So over here, I graphed the property of, when you multiply a log and you multiply an exponential equation, it said you just get x. And so that's what I did. I did the natural log, which is log base e, and then I did e to the power of x. So multiplying them together just got me x, just like what the property said. And so you see this line, y equals x, and look, I even graphed y equals x, and you only see one line because they overlap, because they're the exact same thing. Another way of looking at it is to graph them individually. Graph ln x, graph e to the power of x. And remember, all inverses are reflections across the line y equals x. And so you see that it's a perfect mirror image across that line y equals x. So there's kind of like a graphical representation of this property, alright? So with that being said, let's just do some examples, okay? I'll explain it the long way and then I'll explain it the short way, and hopefully some way it makes sense to you, alright? Because like I said in previous videos, logs are a confusing concept, but the math associated with them is actually pretty easy. So 10 log 4, and we're simplifying it using inverse properties. Alright, so in the previous, when I introduced logs to you in, I guess, part 1, I mentioned that if there's no base for the log, it was assumed to be 10. So it might help, while I'm explaining this example, to write this as 10 log base 10 of 4. Alright, so look, here's the short answer. According to that property above, right here, like I said, these just cancel each other out, and the answer is just the exponent. Okay, so 10 raised to the power of log base 10 cancels itself out, and the answer is just 4. Alright, now for me, I like to understand things. I like to understand why. So what I want to do is I want to reference, what we went over in earlier sections. So in part 1, when I introduced logs to you, I was like, they follow this pattern. If you have like log base 3, you'd raise it to the power of 4 and it'd equal 81. So, writing it the other way around in exponential form, 3 to the 4th power is 81. In other words, if you don't have it equal to something, if I just had log base 3 of 81, I'm just trying to think of 3 to what power equals 81. That's what I'm trying to figure out. All right. So, when you're looking at this example, the 10 log 4, it's an expression, it's not equal to anything, so I'm going to set it equal to x. And maybe it'll help if I go back and set this one equal to x, because I did change it to 3 to the power of x equals 81. Alright, so here I was trying to figure out what power should I raise 3 to get 81. And then going backwards, it would be, I'm going to take log base b, a log base 3 of 81, and that'll equal the exponent. So that's what I'm going to do. I'm going to write log base 10 of x equals log base 10 of 4. Alright? Because that's following the similar property of I take this, I raise it to the power of all that, and it'll equal x. That's exactly what this says. Okay? So the nice thing about this is, if you have something on both sides of an equation, it cancels each other out. Like a scale. If I take the same weight off of both sides of the scale's still going to be balanced. So if I take log 10 away from each side, you could divide it out, by the way. I'm just left with x equals 4. Alright, so what did I just do? I just told you the long explanation of why this answer is 4. Alright, that's basically what just happened. Okay, so that's kind of how logs work. I think it's kind of cool once you start to understand them better. To each their own. Maybe you just want to just learn it and get it over with. But that's the power of mathematics right there. So let's do some more examples and see how it goes. Okay, so I have 8 log base 8 of x. So the short answer is I have the same exact base. This is b. This is log base b. So it's the same thing. You're just left with x. So if I were to simplify it, that's the answer, x. Alright? Now, I'm going to give you the long explanation, and I'll spend a little less time on the long explanation this time. So we have 8 log base 8 of x. Alright? And we don't know what that'll equal, so I'll just put an x. Well, maybe I should just write like a different letter since we had x in our exponent. So I'll say equals y. Alright, so using the logarithmic properties, I can rewrite this as log base 8 of y, because you're going to go this to that, equals log base 8 of x. Alright, so I could divide both sides by log 8. They cancel each other out, so it just says y equals x. And so, yeah, y was what I was looking for. It's the same thing, see? So there's the long explanation right there. So looking at part C, it's not as easy as the other two because my base is not the exact same thing as the big number, the big term. So 4, they could cancel each other out if 4 was here and 4 was there. That's what I'm trying to say. So 64 has an exponent, so 64 to the power of x. So, and I have my base of 4. So what I need to do is I need to write 4, I need to change 64 as a product of 4's. Alright, so it's like, maybe that sounds confusing. So let's see here. 4 to the third power is 64. That's what I mean. Like, it helps to kind of know your exponents or just play around. So you see your base. If you see your base and you see the number and it's not the exact same number as the base, you need to start raising your base to a power to get it to become that number. Not multiplying it by like 4 times 5 and like, oh, it's going to be 20 or whatever. No, you need to think exponents here, okay? Because remember, the inverse of this is exponential equation, so we need to be thinking of exponents. So yeah, so start off with like 4 squared, 4 to the third, 4 to the fourth, until you can match this number. So in this case, it was just 4 to the third power, all right? So with that being said, I can rewrite this as log base 4 of 4 to the third power to the power of x. All right. So you don't have to write the parentheses. If you raise a power to a power, it's the same thing as multiplying them together. All right. So I can just write this as log base 4 equals to the power of 3x. And so, like I said in the other explanations, if you have the same base and then you have the same number outside that base, log base 4 of 4, they will just cancel each other out. So the answer would just be 3x, okay? Because this is just simplifying it, all right? It's not an equation. It's not going to say x equals 10, all right? We're simplifying this. So this just boils down to that. That's the takeaway piece right here, okay? So in this next section, we're going to find inverses. So I'll give you an exponential equation or I'll give you a logarithmic equation and we'll go backwards from that. All right. So if we're going to find the inverse of this, it would be easiest to explain by looking back at the definition. So first of all, what do we have? This is 6 to the power of x. This is an exponential equation. All right, so I'm finding the inverse of that. Well, the very first part of the notes says, according to the definition of a logarithm, the logarithmic function g of x equals log base b of x is the inverse of the exponential function f of x equals b to the power of x. So I have 6 to the power of x. That's b to the power of x. I can just rewrite that as log base b of x, meaning log base 6 of x. All right. So the answer is, I guess I'd put g of x, log base 6 of x. So that's what I mean. It's a confusing concept. The answer is really easy. I have 6 to the power of x. The inverse of that would be log base 6 of x. That's it. All right, let's do another example. So with b, a little bit more complicated in that it says ln of x plus 3. And again, ln's the natural log, so it might make better sense to write log base e of x plus 3. And then that's equal to f of x. All right. So remember, when you're doing inverses, it helps to switch the x and the y. I have an x plus 3 in there, so I'm going to rewrite this as, instead of f of x, you can write that as y. So this is, I'll say x equals log base e of y plus 3. That would be the next step, just switching your x's and y's. And you don't have to write it in log base e if you understand ln, but, this is like pretty new to you, so I'm just like, ln means log base e, and it might make better sense to just keep explaining it with log base e, okay? So, yeah, I have x equals log base e of y plus 3. What do I do next? Well, you need to refer to the definition of a log. Remember, you take the base of the log, you raise it to the power of the outside, and it'll equal that inside number. So I have e to the power of x equals y plus 3. Okay? So the next thing I need to do is just get y by itself. So I can just minus 3 And so the answer is simply e to the power of x minus 3 equals y, or equals g of x, or no, I guess inverse technically would have f to the power of negative 1 of x is the proper way of writing that. But yeah, that would be the final answer right there. So now that I think about it, I should change this g of x. The mathematician inside me is telling me to change this g of x and use the proper notation. And the proper notation for inverses, of course, is writing it to the power of negative 1. So yeah, my bad. Oh well, at least I caught my mistake. So let's do, I got two more examples here. I got part C, f of x equals e to the power of x minus 4. So what am I going to do? I'm going to switch my x and my y. So I'm going to write x equals e to the power of y minus 4. The next thing I'm going to do is I'm going to relate it back to the log property. So you would write log of the base, right? E, log base E. And then that's going to equal the outside, the x. And it'll, equal the outside of x. Now I'm saying equals y minus 4. So, yeah, because it's this e raised to the power of y minus 4 equals x. It should always go back in that pattern there. I think I just said it kind of confusing. So now that I've set it up, log base e of x, well, to kind of further your education, that's my job after all, log base e is the same thing as ln. So I'm going to rewrite ln x equals y minus 4. So I'm almost done. It equals y minus 4. Just plus 4 to the other side. So the final answer here is y equals, once you get into y equals, you can change it to the f of negative 1, equals ln x plus 4. And that's it. So if you think about it, this problem looks really weird, but the process was really short. So that's what I mean. The math part is actually not that difficult, but it's the understanding part. Understanding the meaning of all of it is the difficult part. Let's do one more example, shall we? So here we have a similar example to B. You have a natural log. So I'm going to switch the x and the y. So I'm going to write x equals ln y minus 6. All right. And again, if it makes more sense to you, you can rewrite ln as log base e of y minus 6. I think it makes more sense when you're working it out, because I like to see the base, and I know I'm going to raise the base to the power of whatever it equals. So I'm going to rewrite it as e to the power of x equals y minus 6. Alright, because I know that's the pattern of logs. So when it's an ln, I'm not really seeing the base. It's just kind of assumed. So you kind of just, you know, once you get the hang of it, you can kind of skip this middle step. But until that happens, just do the middle step. I think it makes more sense. So anyway, all I have to do is plus 6 to the other side. And so the answer is f to the power of negative 1 of x equals e to the power of x plus 6. That's the final answer. That's going to wrap it up for the notes. Thanks for watching. Like and subscribe if you feel like it. Alright, goodbye.